Okay guys, hello and good evening. Welcome to tonight's session. So this is our second physics session, and what we're going to do this evening is we're going to have a look at how the energies transfer from one form to another. We're going to have a look at what we call the law of conservation of energy, and then we're going to take that a little bit further and we're going to go into some of the calculations around conservation of energy. Okay, so last week we looked at the different types of energy the energy stores, and we're going to continue that a little bit today with how they convert from one type to another. So, as a quick recap from last week, can you, in the chat box, send me through the names of the different energy stores? So the different energy stores, remember we used a little acronym if you weren't with us last week. We use a little, it's not an acronym, is it? It's a mnemonic, excuse me. It's a mnemonic that most kids today learn GCSE energy names. So there is an energy name that begins with each of those first letters. So one begins with M, K, T, L, etc, etc. And if you just want to type them in and hit send, you can put them into the chat or you can send them direct to me, I don't mind. Probably a little bit of fast and furious, if you will. Type them in, send them, type them in, send them. And what I will do is compile this list. Oh, here we go. Right, let's start putting these in. I don't know what that's supposed to say. Spelling's not my strong point, you'll soon learn. I can't talk and write either. Magnetic, kinetic. See what I mean? Oh, Louis, awesome, awesome, awesome. T, is anybody giving me T? That many coming through that you're taking my chat away. Thermal, L, light, awesome. Oh, Chloe's another one that's absolutely on it. I think she might have got them all in there. Light, yes, thank you. G, oh my goodness me, I can't keep up with you. Gravitational. C. Good evening guys, those of you that have just joined. We are just going through the energy types. My goodness me, so many of you this evening, this is awesome. Chemical, S. We are just naming the different types of energy, so the energy stores as they're called. So you can see we've got the first few, we're on his way with them. Magnetic, kinetic, thermal, light, gravitational, chemical. Oh yes, have we got somebody giving me S? Yes, sound. I think between you you've got them all. E. I've got electrical. Sorry if someone has already put it, but can you just give me the other E? Electrical, and just go for it again. Honestly, I can't make my chat box big enough to see all what you've put. Thank you. Yeah, elastic. And my spelling is terrible this evening, isn't it? And last one, nuclear. Thank you very much. Awesome. That many bits going in chat, this is amazing. Thank you guys, brilliant. So there's a quick recap. So we looked at these different types of energy last week. So as I said, as I was just having a chat to the guys that were logged in before we got going, this evening we're going to have a look at the conservation of energy. So what we're going to do tonight is we're going to take those energy transfers and we're going to look at what types of energy they transfer into. So what do we start with, what's our input energy, and what do we get out of different devices. That's then going to lead us on to efficiency. Okay, not going to say too much about them yet because I've got plenty of questions that I want to ask you guys. So we're going to talk about the conservation of energy. Now, who can put me, and I don't mind if you want to come off mute, if you pop your hand up if you're happy to come off the mic, or you can put it in the chat. You do what you are comfortable with. Can you explain to me what I mean by the conservation of energy? Doesn't matter if you don't get it right. Oh, Megan was on it. Boom. A little speed type as you, aren't you? Okay, so Megan's kicked us off with energy cannot be created or destroyed. Yeah, perfect. Thank you, Oscar. So if we can't create or destroy it, what can we do with it? Yes, I like it. We can transfer it. Yes, good. We can transfer it from one type to another, can't we? Fantastic. Yes. Oh, I like it. Can be transferred and lost. That's jumping into the next little bit. Yeah, super. So energy cannot be created or destroyed. It can only be moved from one store to another. So we can only change it from one type of energy to another. If you want a title as such, conservation of energy and efficiency. So yeah, we can only change it from one type to another. So as I said, what we're going to look at this evening is what are they changing into, and then who said somewhere away that some of it can be lost. We're going to look at that as well because that links into efficiency. Brilliant. Okay, so we're going to have a look at, first of all, how do we calculate these energy changes? Okay, so we're going to have a look at what we can do in terms of numbers and think about what is going on in these energy changes. So there are two types that we're going to have a look at. Oh, gosh, guys, I'm just trying to rearrange my other screen so I can actually see everything. Because the chat box is now that big. It's amazing, but there's so much on here. Okay, right, so absolutely, as you've told me, we can only transfer energy from one type to another. And we started looking at this a little bit last week in terms of, we looked at that we could be heating by particles, heating by radiation. We can have mechanical work done by forces, which we're going to have a look at, and then we've got electrical work done as a current flows. So this one, just to kind of set the scene for you before we get into these calculations. So this is mechanical work. And this is mechanical because it's done when forces act over a distance. So here we can see, and this image did kind of make me laugh when I knew I wanted to kind of have a person pushing a box. That doesn't look like it's putting much energy in, does it? Did make me chuckle. It's either a really light box or they're not actually putting much energy into that. So that energy transfer is a mechanical energy transfer because we're doing that work. Now, what type of energy store is that person using? What energy store, so what energy type is he using? So we're using a force, we're pushing that box. Yes, good. Yes, brilliant. So this person is putting in kinetic energy because they're using their movement, aren't they, to move that box. And then this is a little bit of a weird one. What energy transfer have we got there? What are we changing it into? So what energy store is the box going to get? What energy store will the box get? You're right, he's using kinetic energy to... Oh, I like it. So we've got friction. There's going to be some friction, yes. There's a bigger energy transfer than that. I knew this wouldn't get you. Okay, so yes, let's say we're going to get some friction on the bottom of the box as it's pushing against the floor. But if we're getting that friction, what must the box be doing? Yeah, we will get some thermal, yeah, because of that friction. But he's not going to push against that box and it's not just going to get really hot underneath, is it? Why is it that we get that friction? Why do we get friction when two surfaces... I'm trying to give you clues without telling you. Yeah, right, we're getting there. Yes, movement, collide, rub, touch, all these things. Yeah, we're heading in the right direction. So if the two surfaces, Oscar, you've got it. It's kinetic. It's weird, isn't it? Because this time we've got the same energy star into another, but we've got kinetic. It's the kinetic person of the box. The kinetic energy star of the person, but we're changing that into kinetic energy star of the box because the box is moving along the floor. And you're absolutely right. You're already thinking ahead, moving ahead and thinking what's coming next. Is that there will be, where these two surfaces touch, there will be some friction as we push that box along the floor, and that friction will create some thermal energy. Quite surprised none of you said sound, because if it's scraping along the floor, we're probably going to get some sound energy too. Now we're going to talk about these different types of energy at the moment, because what we want is we want it to turn into kinetic energy, don't we? We want to move that box. We can't help but get some thermal and some sound as well. And in a little while, we're going to look at the calculations first, but then we're going to have a look at when we get onto efficiency. Well, actually, how can I reduce that thermal and that sound? Because I don't need it to make a noise when I push the box across the floor. It's going to, but I don't need it to do that. Okay? Absolutely, yes. Lubrication would definitely, the smoother the surface is, the less we're going to get, isn't it? Perfect. So our first little calculation, I thought I'd start with the calculation bits first while your brains are more awake, before you get sick of hearing me. Okay, so our power calculations then. So we've just talked about this. Sorry, moving the screen. I'm going the wrong way now. So we've talked about this is mechanical work. This is the work done. Okay, so we could calculate how much work has been done to move that box however far across the floor. What we can do is, if we think about something like a vehicle, if we measure the rate at which this work is done, so how quickly are we doing this work, because that's all that's happening in these vehicles essentially, isn't it? We're doing work because we're powering that car along. So what we can do is we can calculate how quickly that energy is transferred, so how quickly that work is done, and that is called power. And so the equation that we need to calculate power, okay, is P equals the amount of energy that's been transferred over the units of time. So how long did it take? Guys, I'll come back to your question of work in a second, no problem. So as I've said before, with excuse me, with your physics equations, make sure you know what the symbols are and what units they're measured in. Okay, so P is okay because that is P for power. It's not always as straightforward as that, is it? Because sometimes when we're talking about current, its symbol is I, but it's measured in amps. So we've got C, I and A. Yeah, so make sure you know what they are. So P is power, and power is measured in watts. Okay. E is the energy transfer. What's energy measured in, guys? Joules, thank you. Awesome. And T is the time, and the time needs to be in seconds. Yeah, thank you. Okay, so we've got, just put your symbols on as well, capital W, capital J and a little s. Okay, sorry, just letting someone else in. So what we're going to do then is we're just going to have a look. A very, very simple, in fact, let me see if I can copy this. Power of technology, eh? Copy that. So we've still got it. And if I can move slide, there we go. If you could just delete that joules for me, please. That would be amazing, so we don't confuse ourselves. Thank you. Okay, so I'm just going to give you that a second. Alright, I'm not going to do anything. And guys, I'll come back to your definition of work in a second. So, calculate the energy transfer if an iron of power 2000 watts is used for 5 minutes. Chucking you in a bit of the deep end here. Chucking you in the deep end. So first thing I would say to you is write out what do you know. So do we know power? Do we know energy? And do we know time? If you want to pop them in chat, if you like, put P equals. Make sure you've got the right size units. Thank you, Sebastian. Yep, so P, we've got our 2000 watts. Oh, Molly, smashed it, yeah. The time, we've got 5 minutes, but we need it in seconds. So we've got 5 times 60, which gives us 300 seconds. Perfect. Do we know the energy? Nope, because that's what it's asking us to do, isn't it? Calculate the energy transfer. So I'm just going to leave it as E. So I'm going to write out what we know, and then I'm going to ask you to substitute it into your equation. So substitute into the equation. So we're going to do 2000. Oh, amazing. Some of you have already gone ahead. Is E over the time, which is 300. Yeah, you've got this. Awesome, guys. So this is where I don't want to interfere with your maths. Yeah, so yeah, some of you are talking about using the bridge method. So you know, you swap it around. Some of you might say, well, we would times both sides by 300 to get that 300. If we're getting the right answers, guys, I'm not going to interfere with your maths. If you're sat there and you're thinking, I've absolutely no idea how to do that, please do tell me and I will show you my way. But I am not a maths teacher and I don't want to interfere with how you do it. If you're getting the right answer, keep going. Okay, so we're going to basically end up with 300 times the 2000, and you're absolutely spot on. We're going to get 6, make sure I get enough zeros. 0, 0, 0, 0, and units, guys. A couple of you put it on. Awesome. Yeah, thank you, guys. Units is joules. Perfect. Brilliant. Okay. Now you did quite a bit of stuff there. If I'd have posed that to you as a sort of format question, I think most of you kind of would have gone, what do I do with that? But because we did it step by step and we broke it down, because you are going to get 1 mark for converting those minutes into seconds. You're going to get a 2nd mark for rearranging. You get a 3rd mark for substituting. And you get a 4th mark for actually getting the correct answer. Could even be worth a 5th mark if the units weren't on there. So could be a 5 mark question that. You've just smashed out a 5 mark question without me sort of really doing anything. Gave you a bit of guidance. Fantastic stuff, guys. Okay, so what we can do, whoops, let's just move me out of the way. So what we can do then is we can use this to compare power outputs. Okay, so if we work out the power of these 2 different motors, so we've got 2 different motors here, we can see represented from that diagram of those boxes with W's on, we've got the weight. See, they're the same size, so they're moving the same weight and they're moving it through the same height. We've got the height labelled on there. So we're moving it through the same distance. It says, but one of them does it in a shorter period of time, and therefore if it does it in a shorter period of time, it must have more power because it's doing it more quickly. Okay, so here we've got an example of two electric motors transfer 40 energies of joules. It's a good job it's half term next week. Transfers 40 joules of energy to lift a load. Motor A does it in 10 seconds and motor B does it in 20 seconds. Determine which motor is more powerful and by how much. Do you want me to pop the equation back on for you a second? Power equals the energy over the time. So I'm going to do motor A and motor B. Yeah, find the power of each. So calculate your power of both, and then decide which is the most powerful. You've calculated the power. Oh, thank you guys, this is whipping through now. Yeah, so I'm going to take the power of motor A, so they're transferring 40 joules, so we do 40 over motor A does it in 10 seconds. Yeah, awesome guys. So we've got 4 watts. Motor B, we're still using that 40 joules of energy. This did it over 20 seconds. And therefore, yeah, sorry, just giving you all a chance to put your answers through. Power is 2 watts, and therefore which one is most powerful? Good, well spotted, yeah. So actually what we want is we want the one with the greatest watts. Yeah, because we want that higher power. It's doing it in less time, so that straight away should say to you, well, if it can do it faster, it's because it's more powerful. Yeah, does that make sense? Right guys, can you just give me, I'm just going to have to expand my screen, can you give me thumbs up, thumbs down? I don't mind whether you can pop it in the chat like Megan has, or I believe you've got it on the bottom of your bar and that will show up on your little picture of the screen. Thank you Zoe, Megan, Oscar, Sebastian, thank you Louis. Yes, we're getting some thumbs up. Happy, happy, happy. Chloe, Molly, yes. Thank you. Awesome. Thank you, James. Thank you, thank you, thank you. Fantastic. Okay then, so what we'll do, let's have a look at a couple of exam style questions, because let's have a look at how is it going to be actually asked to you in a question. So we've got a question here and just a little bit of exam technique. If we look at the question, we can see this one is worth 2 marks. So for 2 marks, the numbers should be there for us. The equation's there, 2 marks. 1 is for substituting the numbers in correctly, and 2 is for correctly calculating. So I would maybe now change your chat direct to me, so you don't tell everybody your answer. And then have a go at question A and B. Shall I make this a little bit easier? Shall I just put the numbers next to here? And you can tell me B is which ones. Thank you, Megan. I've got an answer through already. So if you send it direct to me, you can do it whenever and hit send. Then I can see them coming through. So this is worth 2 marks. Now I've got an answer from Chloe and an answer from Megan, and they've got the same answer. That's a good sign. Thank you, Molly. Also got the same answer. Feeling quite confident we might have got this right. Sebastian's making it a 4th. Oh, this is awesome. So for part B, again, Megan and Chloe, you've got the 2 same ones. Amelia, yeah, you've got exactly the same answer again. Right, we've got most answers through, so let's have a quick look. If you're struggling, I'll model it through for you. So we're calculating the power. Okay, we're told that the work done, the energy, that's fine, Amelia, we're going to go through them all, don't worry, is 120,000 joules, and it does that in 8 seconds. If you've got that written down, that gets you mark number 1. Ozian, don't worry, it's because you've put it straight in the chat, isn't it? It's fine. That gets you mark number 1, and then correctly calculating that it's 15,000 watts gets you mark number 2. Okay, part B then, the power input to the motor is greater than the power output, and this is what we're going to lead into next. So if you've identified these, brilliant. If you're a bit unsure at the moment, that's fine, it will become clearer. So the input, spot on Louis, well done. The power input is greater than the output. So why? What's going on? Why are we not getting the same amount of energy out? Because we've talked about, and we've just defined, that energy is not created or destroyed. So one, some of the energy is transferred in heat in the surroundings, because as that motor spinning, there's going to be friction that will generate heat, and that will just what we call dissipate into the surroundings. And friction causes the energy to be transferred in non-useful ways. Yeah, we don't need it to heat up. We don't need a motor to get hot. We need a motor to move. But wherever we've got 2 surfaces together, like in a motor where we're going to have those cogs and those all linked together, there's going to be some friction. It's going to produce some heat energy, and we're going to lose that. It's going to be classed as a wasted energy. We're going to do a little bit more about that later. Right, let's have a look. Yeah, let's do this one because this is a little bit different, because here you've got to take it from the graph. See if I can just make it a little bit bigger for you. Excuse me. So this one is worth 3 marks because this time we're calculating the work done. So this time we've got to rearrange. The numbers are there for us, but we've got to rearrange it to get the answer. Okay, so don't worry too much about the equation at the moment because we've just been doing that, haven't we? Power equals the energy divided by the time. Or if you've written power equals work done divided by time, that's fine. And then I'm just going to give you a couple of minutes. We'll do the same again. If you're sat there at the moment and thinking, I'm not too sure about this, look at what we know. Find out what we know first. And then this is our equation. Substitute them in, and then hopefully you should see what you need to do. When I was at school, rearranging equations just couldn't do it. Blew my mind. But now that I've been shown it and this is why I will model it for you guys, and I've been shown it. It's much more simple, much more straightforward. These answers are coming through thick and fast. Thank you. Megan, Molly, Oscar, Amelia. Thank you, thank you, thank you. All got the same answer as well. Chloe's got the same as well. This is good. Makes me think that you've probably done it right. Okay, so the power here is 200 watts. The energy, we don't know because that's what we're working out. And the time is 1800 seconds. It's already in seconds for us, so we don't need to do anything. So we've got 200 equals energy over time, 1800. So if you've got that far, that's 1 mark. Now what terminology you're probably going to use here is that if you times both sides by 1800, it's going to cancel it out of this side, isn't it? Because times in a divide. So we're going to end up with 1800 times 200 equals the energy. If you've got to the rearranging stage, that's mark number 2. And then I'm going to trust you guys. 360,000 joules for mark number 3. Awesome. Awesome, awesome. Right, I'm just going to expand my screen again so I can see everybody. Before we move on, can we just have another quick thumbs up, thumbs down? How are we feeling? I don't know if there's a thumb like that. Give me a little face, thank you. Amazing. Loving all these thumbs up, guys. Awesome, thank you. Good. Okay, give you about 30 seconds, then we need to move on. Okay, so what we're going to do now is we're going to start and look at those energy transfers. So we've talked about conservation of energy is we can only transfer energy from one type to another. We can't create it or destroy it, so we've got to have it, and what does it turn into? And then we're going to move that on and look into the efficiency. Now, some of you have already started with those ideas that we're losing some energy as thermal energy, etc. Okay, so we're going to start with this TV. You're most welcome, no problem. And what we're going to do is we're going to think about what energy store goes into the television and what energy store do we get out. Okay, so in the chat box, if you want to put in and out, tell me what are we getting in, what are we getting out, and I will annotate as you through. Okay, so I'm going to put an arrow in. Well done, Amelia. Electrical in, yes, definitely. I put a plug on the TV so that you identified that. It didn't have a plug on. I had to put that on myself. Brilliant, yeah. So, electrical in, what are we getting out? Okay, we're getting some sound out, absolutely. So we can hear what we're watching on the telly, can't we? We're going to get some light out. That's how we see what's on the telly. Yep, sound, light. I'm going to go with that as well. Some thermal. I've no words, Megan. I've no words. I probably should have labelled it, shouldn't I? Oh, that's going to tickle me. Just to clarify, this is a television and not a microwave. My bad. I probably should have labelled it, shouldn't I? Okay, next little challenge then. So sticking with our television. So I want you to now identify which are the useful energies and which are wasted energies. So which are useful and which are wasted. So what do we need that device to do? Brilliant, yeah. Good. So I'm going to box them off in green. So sound and light are useful. I'm going to change this to red. Good, yeah. And the thermal is wasted. We don't need our television to get warm. We need sound and light from our television so that we can enjoy our shows that we're watching. We don't need it to get warm. Okay, brilliant. Now we're going to come back to these in a minute. We're just going to practice this little skill for a moment. And I will tell you what devices they are. So here we have an electrical heater. And I did quite like this because I don't know why, but I can just see a face in this little electrical heater for some reason. So we've got an electrical heater. So again, let me know what energy goes in and what comes out. Just on his nice little face. There's his two eyes, there's his little nose. And we have a gas stove. So that's something like that you might take camping. Good. Good, so we've got electrical in. Brilliant. Oops, write that a bit wonky, doesn't matter. Thermal. Light. Yeah, I'm going to go with that as well. Okay, what about my little gas stove? Yes, thermal and heat are the same things. Thermal is the correct term, correct type of energy, but yes, heat. In. Oh, Amelia, you're on the heater. Okay, onto the gas stove. What type of energy are we putting in? And what comes out? Good, yes. Awesome. Super glad you noticed that. Chemical in. Out. Thermal again, yeah. Yeah, we're going to get pretty much the same out with it. There are two kinds of heaters basically. But I put the gas to see if you'd identify. Yeah, I might get a bit of sound. Okay, so we've got very similar. So same again for me guys, identify which is the useful and which are the wasted. Which is a useful and which is a wasted. I'll go from a green, from a useful. Sound, is that a useful or a wasted, Chloe? Useful is thermal. Yeah, I'm just going to recreate them on both. Yes. Light and sound are wasted. Now, do you know, we could argue that that light is quite useful. Yeah, we could say they're a bit useful. But do we actually need that heater to give off light? Yeah, and it's we can kind of argue it, you know, but we don't need it to do that, do we? If it didn't give out light, it would give out more thermal energy, more heat energy, and that's ultimately what we want, isn't it, from a heater? We want it to get hot. We want the thermal energy. Yeah, it's not its main use. it is, I agree, if it was dark and what if you're camping, it could be useful, handy, but it's not what it's intended to do. So when we then apply these to efficiency, what we're going to look at in efficiency is how much of that energy do we put in does come out as useful energy. Because if we have a choice of two appliances, what we might do is want to look at their efficiency. Because if we look at their efficiency, we know that most of the energy that we put in is going to come out as a useful energy, and therefore we're not wasting it because we're paying for that electricity, we're paying to power that device, and therefore we can make a decision on which one we choose. Okay? So moving it on to efficiency then. Oh, we've already covered wasted energy. Already kind of done that. Whoops. Where have I put my slide? No idea. Okay, I'm going to change this. I'll change this to efficiency. Do you know how you calculate efficiency? Do you know how we calculate efficiency? Nope, that's fine. I like it. No, I don't. It is a percentage usually, yeah? Good. So the efficiency of a device is the useful yeah, brilliant. It's the useful output divided by total energy input. Yeah, so the total input multiplied by 100 to get it a percentage. Yeah, awesome. Oh guys, you're on this. You're on this, aren't you? Right, I'm just going to copy that so that we can take it with us if we need. Okay. So before we jump into looking at efficiency then and doing some actual calculations, one thing I just want you to think about, we'll come back to that one in a second, is how can we reduce that energy loss? And I can't see back in the chat that far, but somebody said earlier, when we're talking about the box sliding across the floor, and there's a little picture clue, how can we reduce energy loss? Good, yes. Lubrication, absolutely. So we're reducing the friction. So if we reduce the friction, so if we use the lubrication, we reduce that friction, we reduce that heat loss. Brilliant. Whoops. Oh, I can make that into an O, can't I? Get away with that. Brilliant. Let me think how I can give you a clue to something else. If it's really hard to try and think how I can give you an example. Let's say you're pedaling along on your bike and it was rattling away and your wheels were wobbling a bit and your handlebars were wobbling a bit. So yes, we can oil it. That's the same as our lubrication. I don't think I'm going to be able to give you clues enough to... So if we've got something rattling that shouldn't be, and that's making sound energy that we're losing that maybe we don't need to, what could we do with it if something was like rattling about and it shouldn't be rattling about? Yeah, so anything squeaky, any two surfaces together, absolutely. We could add oil or buy a new one. Okay. Or what we can do is we can make sure, yes, love it, well done Amelia, yes, tighten loose parts. That seems crackers, doesn't it? And that's something really quite tricky to think about. But if you've got, I can't even think of something that would have screws in. If you've got something held together and it's got screws in, and those screws aren't tight enough and they're rattling, that's generating sound energy. Yes, it's probably going to produce some more friction as well because you might have that movement, but actually if we tighten those up so that those parts don't move that are not supposed to move, then what we can do is, if we haven't got that rattling, we're not losing that energy as sound. Does that make sense? Just give me a yes or a thumbs up if that, because that one, that tight and loose parts, if that makes sense. Thank you. Thank you, thank you. Yeah. That's a really sort of higher level thinking, is that most common one and the most obvious one, absolutely reduce that friction, stop that squeaking. Yeah, so I will just say it again, no problem. So if we've got a device and it's moving, and if it's rattling because something isn't tight enough on it, so it's not holding place and this panel's rattling away, that's generating some sound energy. And that's sound energy that we don't need. So that's a wasted energy. So if we were to tighten those screws and stop that part from moving and rattling, we're not losing that sound energy. And so we're making it more efficient. I wonder if that makes sense. I'm just going to move my slide while I'm watching the chat. Quite surprised we've still got that. Yeah, that's what we're doing. We're conserving that energy. Yeah. Yeah, absolutely spot on. Right then guys, let's have a look at a couple of efficiency questions then, a couple of calculations just to finish us off before we do a quick quiz to finish the session. So this question, again, look at it, we've got 2 marks available, so it should just be a matter of substituting the numbers in and calculating our correct answer. Now here we've got total input into a pumped storage power station. Don't worry what it is, don't worry if it's in watts, if it's in joules. One thing that we just need to do is we need to make sure that the units are the same. And it tells us that the total power input is 600 megawatts and the useful output is 540 megawatts. And because they're both megawatts, we can go ahead with the calculation. If those units were different, we'd have to convert one of them so they were the same before we did the calculation. But we'd probably get a clue in the marking because it'd probably be worth 3 marks because it's asking you to convert as well. Okay. Oscar, Megan, Zoe all got the same answer. Perfect. Again, when we get in the same answer, it's probably because we're doing it right. Or I've told you it completely wrong. It's because you're getting it right, guys. Chloe, another one. Awesome. Brilliant. Good, yeah. So our efficiency, useful output is 540 megawatts. Oh yes, you're all getting the same answer. Divided by the 600 total input, multiplied by 100 to get an efficiency of 90%. Perfect. Brilliant. Okay, let's have a look what other examples we've got. Okay, so here then. So calculate the efficiency of the motor in test D. So this time you've just got to take the information from the table this time. Do you want the little, do you want the calculation again, or have you got it, guys? I'll take it, shall I? So I'm just going to hang fire and let you roll with it. Remember, you can put your answers in chat or you can send it direct to me. It's entirely up to you. Thank you, Molly. Thank you, Zoe. Thank you, Chloe. Ah, I like it, Megan. It's what I call a sensibility check, that. It's quite a few of you have sent through now, and you might be sat there, you might have calculated 150% and gone, that can't be right, we can't have more than 100%. You are right. Why is that right in this case? Why is it right in this case? So for those of you that are wanting modelling, just in case you're a little bit stuck, we're going to go for the useful output. So we've got the electrical input and we've got the power output. So we've got 120 over the electrical power input is 80, and then multiplied by 100 gets you 150%. And some of you absolutely now, this is brilliant, this, because some of you now are going, well, that can't be right, we can't have 150%. Yeah, there's more useful than what we put in. Look at the question, look at the line above. What does it tell us there? This is where it's see who's been observant and see who's read all of the question. I like your thinking, Zoe, but it's not because it's overworking. It does tell you in that question somewhere. It's a big clue. Yes, well spotted, Amelia. Yes. It tells us here, look, the result for test D is anomalous. Sneaky, that question, isn't it? Because you've done that, you're all exactly right. You calculated your 150% and you went, hang on, that can't be right. We don't have 150%. But it does tell us in the line above that the result for test D is anomalous. Anomalous means it's not right, it doesn't fit the pattern, there's something not quite right with it. And so because it's telling us that it's anomalous, when we get a reading and we get our answer and it's like, that's not quite right, but it's okay. Yeah, it's something that they've done in their readings, in their testing. So they've probably read that reading wrong, put it into that table wrong, and it's kind of saying to us, we know it's anomalous, but then calculate it, because it's still just wanting you to show that you can calculate the efficiency. But what most people do then is have that little bit of a panic, because you do what I call a sensibility check. You check it and you go, well, I can't have 150%, it doesn't make sense. Okay then, guys, right, let's just finish off then. And I always do 10 of these, but we haven't probably got 10 minutes worth to do them. And I'm tutoring next, so I will reduce it to 5. So if you would please, and make sure that you're sending it direct to me if you're going to send it sooner, or you can set it up and hold on. Okay, I'm just going to put number 1 and whatever letter, number 2, whatever letter. I'm going to have to be quite strict on time. I'm going to give you 2 minutes. 2 minutes, so like number 1 you tell me is A, B, C or D. Number 2 is A, B, C or D. Good, good, good. Keep them coming, keep them coming. Thanks, Molly. Thanks, Megan. Thank you, Amelia. Thank you, Oscar. Thank you, Zoe. And again, I'm liking this because most of you have got exactly the same, which makes me think got it right. So I'll go through this nice and steady. I see some people like it. Question 3. So number 1, the principle of conservation of energy states that energy cannot be created or destroyed, only transferred. No problem, Ethan. Thank you. So 1C. 2, when energy is transferred in a system, what usually happens to some of the energy? Some of the energy will often dissipate as thermal energy, so 2C. Well done, guys. What is the equation for work done? So work done is the energy over the time, so it's A. Well done. CCA, yeah. A machine has an efficiency of 75%. What does this mean? 75% of the input energy is transferred usefully. 4B, awesome. And which of the equation correctly calculates efficiency? It's the useful over the total. Therefore, it is A. Well done. So we're C, C, A, B, A. Thank you, Louis. You too. Right then, guys. If anybody's got any quick questions, I can answer those. Oh, you are more than welcome, Molly. Awesome stuff, Oscar. 5 out of 5. Seb, you are most welcome. Which one, Megan? Which one could be C as well? You're welcome. Thank you, Isaac. Thank you. Last one. Yeah, I'll give you that. Yeah, you're most welcome, Chloe. Thank you. You're most welcome. Thanks, guys. Thank you.